In this presentation, I will talk about a method for comparing spatial point patterns. This is joint work with Jim Klosowski. Let me start with a motivating example. Here on the right, you can see a map with locations of lung and larynx cancers shown. This is a classical dataset from Peter Diggle. At the bottom here, there's an industrial incinerator. And the substantial question here is whether the incinerator has an influence on the incidence of larynx cancer. Peter Diggle, when analyzing this data, he takes lung cases as a surrogate for susceptible population. So the assumption here is that the incinerator does not have any effect on the lung cancer. He models these point patterns as inhomogeneous Poisson point processes. So these have intensities, one for larynx and one for lung. And then if there is an effect, then the ratio of these intensities would be non-constant. Again, remember, lung cancer cases are not affected by incinerator, so it only could have an effect on larynx cancer cases, so the ratio would vary in the space. And it would be ideal if it would depend on distance to the incinerator, and that would provide a conclusive proof of the effect. In this presentation, I will focus on answering question number 1. So given 2-point processes P and Q, we would like to test the null hypothesis whether their ratio is constant over the domain. We can also express this as asking whether P and Q have the same functional form or dependence on the spatial variables. Classical tests would go and test for equality of the intensities, but that would mix the location pattern with the total number of points in the pattern. So, for example, in this cancer case, you will see that it's really easy to reject the equality hypothesis because there's so many more lung cases than the larynx cancer cases. So it should be clear now that what we're really looking for is the ratio, and we want it to depend on the coordinates. We can normalize the intensities by dividing them by the integral of the intensity over the domain, and this way we would get probability distributions. We can refer to these probability distributions as distribution of the event locations. We can refer to these probability distributions as the distribution of event locations. The null hypothesis conveniently turns into the equality of these two distributions. So the nuisance parameter is gone, and we're left with two-sample problem. And when I say two-sample problem, this is not the equality of means, but rather the question is whether given two samples, we need to determine that they are drawn from the same distribution. Existing approaches to spatial pattern testing, let me list some of them. There's many more approaches. For example, if you look at classical work of Diggle and his collaborators, you'll see that they estimate the logarithm of the intensity ratio, and they come up with a bootstrap or resampling method in order to test null hypothesis. There's been more interest recently. For example, Zhang and Zhuang, in a very recent paper, they introduced a Kolmogorov-Smirnov-like comparison. And then Fuentes-Santos et al., they take the kernel density estimates of P and Q and compute the L2 distance between them, and then they use it as a test statistic. In general, of course, we can go with the general two-sample methodology. So if we look up in the literature, there's so many methods for measuring the divergence between two distributions. Some of those popular ones are maximum mean discrepancy, the Wasserstein distance, there's energy distances, and so on and so forth. You can pick any of this and apply to the problem. But what is the main issue here? There are a number of issues. The one issue is that in order to compute the p-values, you need to use resampling, except for the Zhang and Zhuang case. And this becomes a problem when you're testing at an industrial scale where you want to make multiple comparisons, and then you need p-values at a very granular level, and that means that you need to run many simulations to actually compute those p-values. This could be a problem if you're doing a visualization and you need a real-time response. And also, there's been a lot of interest in alternative measures to p-values, such as Bayes factors, but none of these methods provide such an alternative measure of evidence against the null. And also, these methods do not support replicated pattern comparisons, where you could have two sets of patterns that you want to compare. For example, crime patterns on Mondays versus the crime patterns on Wednesdays. Our inspiration comes from the maximum mean discrepancy. This goes back to the work of Arthur Gretton and collaborators. So this is, as I mentioned, this is a notion of dissimilarity between probability distributions. And some people might be more familiar with distance energy, with the energy distances. So the formula is very similar. You're taking some quantities based on the expectations of a two-variable function. So if it was an energy distance, here you could take the distance between the 2 points. But in this case, for maximum mean discrepancy, you actually have a kernel. You can, for example, pick the Gaussian kernel, and then you compute those 3 expectations. And if you look at the terms, there's the first and the last term. They sample the points from the P and Q separately. But then there's a middle term here which samples 1 point from P and then 1 point from Q. If you look at this a little bit, it's kind of clear that if P and Q are equal, then the MMD would be 0. It turns out that the opposite is also true. If MMD is 0, then for a very large class of probability distributions, it would be true that P equals to Q. A very important property of maximum mean discrepancy is that there's an embedding of probability distributions where the Euclidean distance in the embedding space equals to the maximum mean discrepancy between those probability distributions. The problem with this embedding is that it's infinite dimensional, and then there's no explicit formula for the embedding itself. We got inspired by that kernel mean embedding, but we wanted to have a finite dimensional embedding, and we wanted to have explicit formulas. So what we propose is an approximate kernel mean embedding. What we do is, given the point patterns, we embed them in a finite dimensional space, and we call this embedding ACMA. And then our goal is to make sure that the Euclidean distance in this embedding space is approximately equal to the maximum mean discrepancy. Our construction is related to the random Fourier features of Rahimi and Recht, but they're custom tailored to two-dimensional setting in order to give better accuracy than RFF for the same number of dimensions. We inherit the consistency from MMD, and now we also have this interesting choice. We're not limited to testing based on Euclidean distance, which would have been MMD squared approximately, but we can pick any statistic in this finite dimensional space that allows us to compute p-values in a simple way. Now let me go over our approach. There's 2 steps in the approach. The first step is computing the approximate kernel mean embedding. You can concentrate on the pictures on the right here. The pattern itself is this blue square with the dots in it. There's the blue dots, x1 through x4. So given this pattern, we'll pick a line. In this case, it's this red line, dashed line, which we call VI. And then we'll project these points on the point pattern points onto the line, and we get this red dots on the line here. Then we pick a circle of a certain radius, and we'll wrap this line onto that circle. And then this gives us corresponding angles, and then we can rescale the circle, keeping the angles intact to have a unit circle. This is equivalent to computing cosines and sines. Having computed, as soon as we have the cosines and sines, what we do is we take the mean of the sines and cosines. And this means that we're going to get 2 numbers, one for cosine mean, and then another one for the sine mean. And this is going to give us a fingerprint of our point pattern in the given direction of the line, and a given scale which depends on the circle radius. We repeat this process with several more lines and radii, and the choice of these lines and radii is guided by our constructions in order to make the resulting embedding Euclidean distance and the resulting embedding space as close as possible to the maximum mean discrepancy. So we obtain a d-dimensional embedding where d is twice the number of lines times the number of radii. I want to bring your attention to an interesting fact here that will be useful when doing the tests. Notice that every point in the pattern has a corresponding embedding in this d-dimensional space. The acme itself, which summarizes the point pattern, the entire point pattern, is the center of mass of this individual embeddings, which is shown here with a blue cross. Now, as we said, because of the connection to the maximum mean discrepancy, our original test boils down to testing whether the acmes are equal. A nice thing about construction is that acme itself is a mean, so we're testing for equality of means. And here you could think we could just go ahead and use classical tests such as Hotelling's t-squared or newer tests that work in high-dimensional settings. Unfortunately, these approaches do not work. There's two problems here. For example, if you start using Hotelling's t-squared, you'll quickly find out that estimating covariance matrices is unstable. One obvious case where this happens is where the number of points in the point pattern is smaller than the number of dimensions. But also, this happens for another reason. The data itself, the resulting embedding, is not Gaussian. It's not normally distributed in that high-dimensional space. There's nonlinear functional relationships between the coordinates. You might remember that there were sines and cosines involved there, and obviously sines and cosines lie on the circles, but also there's higher-order relationships between the coordinates as well. So we actually tried these two methods, Hotelling's t-squared and Chang and Gin's method, and they were not able to control the size of the test. So we go for a different approach. Remember, our goal is to be able to compute the p-values easily. So what we do is we apply two sample t-tests on each coordinate of the embedding. This way we're going to get p-values for each coordinate, so there's going to be d of those p-values. At this point you might say, okay, I'm done, right? We have a global null hypothesis of equality, and then what we can do, we can take those p-values and use the Bonferroni adjustment, and if any of them gets below the threshold, the adjusted threshold for p-value, then we reject the global null hypothesis. But what we wanted to really do was to be able to do multiple comparisons. So in a sense, so we have many pairs of point patterns that we want to compare. So we really need, for every comparison, we need a single p-value, not d p-values. At this point, we decided to combine those p-values. But the classical approaches do not work. For example, if you try Fisher combination, it's not going to work, because this classical approaches assume independence between the p-values. Turns out that, and it's kind of obvious that there are dependencies between the tests that we're doing. When a t-test along a line, along a given line direction and scale detects a difference, a statistically significant difference, then it's very likely that we're gonna see that type of difference along other dimensions of the embedding. So there are positive dependencies between the tests. Fortunately for us, there's been a recent work on combining p-values. One of them is harmonic mean combination, and the other one is Cauchy combination. We show in the paper this combination methods actually work very similarly for small p-values. You can go and check our archive preprint for this paper. But let me mention one thing. For example, in harmonic combination, what you do, you take the harmonic mean of the p-values. And if you think about it, you'll see that when you compute harmonic means, the smallest value has the largest effect. So if one of those p-values is very small, then that's going to dominate the resulting p-value, which is good in terms of power of the test. Another interesting result of the simple approach is that we can actually compute something we call mean Bayes factor. The idea here is that for every t-test, we can compute Bayes factor using default priors. And this has been implemented in our libraries for a long time. So we take those Bayes factors, we combine them using just simple arithmetic mean. Turns out that this is optimal approach, and this is again based on a very recent work of Wolfgang Wang on arXiv. So does this really work? So what we do here, we start with simulations. We start with inhomogeneous Poisson processes. And on the right, you can see a table where there's some parameters here. Let me just tell you that here, when beta 1 and beta 2 become larger, the pattern becomes more complex. There's also, we also change the number of points in the patterns. And then if you look at the size, which is the top part of this table, and let's concentrate on the results for our paper, you'll see that the size matches the nominal level very well. And then if you look at the power, which is the bottom part of this table, you'll see that as the number of points increases, the power increases and almost becomes 1 for these examples. We also compare our method to the only previous method that does not require resampling to compute p-values, which is Zhang and Zhuang's method. In terms of the size, their test a little bit more conservative, so it's not surprising that there's slight difference between the powers, but I think they're almost the same with our test. But then we notice this interesting part where as soon as our point patterns become more complex, we see that their method does not, the power of their method does not converge to 1. We also test this method on non-Poisson processes. Notice that our methods do assume that the processes are Poisson, but let's see what happens here. Here on the right, we're looking at the size. There's two types of the processes that we tested this. There's hardcore process and there's clustering process. In hardcore process, the idea is that the point pattern will have points no closer than a certain radius. And as you go to a larger radius, this is denoted by 1, 2, 3 here. So, and in this case, you see that as the radius involved in the hardcore process increases, our test becomes more and more conservative. The cluster processes is the opposite of the hardcore process in the sense that in order to generate a cluster process, you start with just a regular Poisson process, but then for every point in the Poisson process, you actually add a cluster of points. And the index here, cluster 1, cluster 2, cluster 3, it captures how many points you're adding. And if you look here, you will see that our size becomes much larger than the nominal size. But then this is really expected. If you think of this t-test, the samples within the point pattern, they're not independent. So maybe we could fix this problem by considering something that's been called effective sample size. So we do a very simple correction in the paper. What we do is we divide the total number of points in the point pattern by average per cluster count. And this way, we run the same t-test, so only the number of points now has changed, or effective sample size has changed in the t-test, and we see that we're matching the nominal size very well. This is actually very useful because you might be collecting correlated data, so it could be locations from the same user, and it's pretty easy to define effective size in that case. It's going to be the number of users in your data set. As I mentioned, our method can be used with replicated point patterns as well. Here, a nice feature of our method is that you don't need the Poisson assumption, but then there's another assumption, technical assumption, that can be checked using domain knowledge. And again, in this case, you can see that our size and power work out well. Now let's talk about the applications to real-world data. So I'm going to start with looking again at the original example that I gave you in the first slide. So in this case, the p-value that comes out from the comparison of the blue and red point patterns here is pretty close to 1. And then the Bayes factor, the mean Bayes factor, is much smaller than 1. So we could say that we can safely retain the null here. And this is in agreement with the previous reanalysis of this data, notably by Peter Diggle himself. Another application we did was to look at a year of data from Chicago crime data set. In this case, you have for every crime type in that data set, and every day of the year, you get a pattern, a point pattern. And what we want to do, we want to compare point patterns for different days of the week. And specifically, we took our goal comparison was compare some weekday with a weekend. So we picked Tuesday versus Saturday. But we also wanted to have some check or some kind of control. So we also compared Tuesday versus Thursday. The idea here was that we don't, because Tuesday and Thursday, they're in the middle of the week, we expect no difference between them. And between Tuesday and Saturday, there might be some differences. So we run our test, and then you can see here that for Tuesday versus Thursday comparison, there's no hypothesis that got rejected. And here on the right, for Tuesday versus Saturday comparison, you will see that there's a number of comparisons that get rejected. Let me note that the rejection here is based on the Benjamin-Hochberg procedure at the FDR level of 0.1. And then here you can also look at the Bayes factors, and they're also useful in interpreting the results. For example, if you look at the Bayes factors for the top 2 differences, the theft and battery, they're pretty large. And based on Jeffrey's rule of thumb, you would say that there's a strong evidence against the null. For deceptive practice, by the same rule of thumb, you would say there's substantial evidence. But then for the last one, for criminal damage, you'd say that it's not really worth mention or barely needs to be mentioned. So to summarize, in our paper, we introduce a method for point pattern comparison, which works for inhomogeneous Poisson point processes, but in addition, it works for non-Poisson processes if you can estimate some kind of effective sample size. And it can do replicated pattern comparison for a very general class of processes. A nice result of our method is that you actually also get a strength of evidence, a notion of strength of evidence. Our mean Bayes factor can be used to judge evidence against the null, and this is in line with recent suggestions on reproducibility, some of them which call to replace p-values by Bayes factors. Our method is also highly efficient in terms of computation, because each ACME can be computed separately and independently for a pattern, and for the testing, you need only some summaries of ACME per dimension. Remember, we're doing t-tests per dimension, so you just need the number of points, the mean, and the standard deviation. And that's it. Thank you. You can check out our paper on arXiv.